Now, resistance is an interesting topic in physics. It suggests, if you've read about it, I asked you to look at Ohm's law and stuff like that. If you've read up about it, you'll know it's to do with a link between current and voltage. Well, if you're learning about electricity, actually that's quite a dangerous idea. It's when people muddle up voltage and current, when they start thinking voltage behaves a bit like current, or they start thinking electricity is just stuff, and it isn't separated into two key ideas, that's when people misunderstand electricity. So you need to be careful with resistance, because it's kind of suggesting a link between voltage and current, which isn't really there. Okay? In terms of what resistance is, I'm with the Borg and Star Trek on this one. What did the Borg say in Star Trek? Resistance is futile. Okay? Let's put that up there then. Resistance is futile. We'll see in a moment why, as a physics concept, it's not quite as shiny as some other things that you study in physics. Okay? As a physicist, you kind of need to treat it with a little bit of care. Anyway, voltage and current is what we've been looking at, and last time I asked you to investigate the link between voltage and current. You'll remember you set up a circuit where you had a light bulb and you changed the voltage and looked at what the current was. Then you did the same thing with your resistor, where you changed the voltage, looked at what the current was. Okay? Now, generally what you get for something like a light bulb or anything which is a metallic conductor, in other words, something that's made mostly of metal, then you would get something like that. Okay? Your curve may be steeper or flatter or something like that, but that's normally the shape that you get with something like a light bulb. Okay? For a resistor, then what you tend to get is a fairly straight line. Okay? Now, what does this suggest? Well, as a physicist, it suggests to me that actually there's no one definite connection between voltage and current. Okay? It's not like drawing a graph of something like distance against speed. If you go at 10 miles an hour for an hour, then you'll travel 10 miles. If you go at 20 miles an hour, you travel 20 miles. If you go at 30 miles an hour, you go 30 miles. And if you drew that graph, it's absolutely straight. And if you went at 50 miles an hour, then you just get another straight line with a different steepness. This is really interesting because this suggests actually the link between voltage and current would depend on which device you're using. If you're using a light bulb, then it's a curve. If you're using a resistor, it's a fairly straight line. And there are other devices which can give you other shapes as well. So the interesting thing about the link between voltage and current is it's clearly different for different things, all right? And that's not normally what we deal with in physics. Physics is all about the truth of the universe, things that are absolutely true, like Newton's laws of motion and Newton's law of gravity and stuff like that. So the first thing I'd do is draw to your attention like an important health warning with voltage and current. And I really don't want you to start muddling the two up. I don't want you thinking if you put more energy in the trucks, they go faster. Because that doesn't quite work, does it? All right? The good work you've done so far in separating out voltage and current. When I say current, you're hopefully thinking how many trucks per second. When I say voltage, you're hopefully thinking how much energy is being taken out or put into a truck. Two separate ideas. And if you're thinking, well, why has he made us do that experiment? Because I can't see there be any link between voltage and current. You're kind of right. Because actually you get different results depending on which object you use. Now, Newton said gravity pulls things down towards the earth, and if I drop this pen, that's true. Do I need to check that it works for this other pen? I really don't know if I can try it. Same sort of thing. What about glue sticks? Could glue sticks be different in the way that gravity works on them? Afraid not. Okay? And this is the reason Newton's law of gravity, or as the sixth one will tell you, Newton's law of universal gravitation, we can look at galaxies on the remotest corners of the universe. Corners of the universe? And what do we see? We see Newton's law of gravity at work. Okay? That's a really impressive piece of physics because you've got one law which applies for pretty much everything. Okay? Can I warn you straight away, perhaps put a health warning thing. Can I just warn you then that we're heading into an area of physics where we're getting different results for different things. Now think about all the physics you've ever done Physics doesn't normally work like that. Newton's laws of motion, Newton's laws of gravity, pretty much anything you want to think about, you get the same thing for all sorts of different objects. Okay? Anyway, let's push on. So the question is then, what is the link between voltage and current? And we're a bit stuck. Because you might say, oh, the link between voltage and current is a nice straight line. But actually, so the question is, what do these results tell us is the connection between voltage and current? And allegedly, the answer to that is the thing I asked you to look at for homework, which is Ohm's law. Okay? Now, Ohm's law says basically voltage against current is a perfect straight line. Okay? It says this is the link between voltage and current, that the graph is a perfect straight line. You should have got something like that for your resistor, but your light bulb will almost definitely have given you something with a curve. Okay? So, if we have a look at these results, then you can see this doesn't look quite right, but we'll go with it anyway. Ohm's law says voltage and current are a perfect straight line through the origin. Now, in physics, and this is something you will need to jot down, and in any subject really, when you see two quantities giving a perfect straight line through naught naught, there's a special name for that, and that's called proportional. Okay? So this is basically what Ohm's law says, which is that voltage is proportional to current. That's basically Ohm's law. Okay? And what's his evidence for that? Well, he says, well, if you draw a graph of voltage against current, then you'll get a perfect straight line. And a perfect straight line, and this isn't just physics, any subject, if you draw a graph of elephants against penguins, and you get a perfect straight line through naught naught, it means the number of elephants is proportional for some mad reason to the number of penguins. Okay? So this is really important. Can you get those two linked up in your notes? Perfect straight line through the origin means the two things must be proportional. Okay? The good thing about things being proportional is that gives us a handy formula. Okay? Proportional means there's going to be a simple equation that links them together. Okay? And the equation goes something like this, voltage, current, and we introduce a third quantity, which is resistance. Okay? Voltage you know all about, it's measured in volts. Current you know all about, it's measured in amps. Resistance you may not be so familiar with. It's measured in ohms. Kind of guessed it would be, wouldn't it? And the symbol for the ohm, we obviously can't put the letter O. Current is measured in amps, and we put a capital A. Okay. Resistance is measured in ohms, and it's the Greek letter omega. Funny sort of top hat thing, like a sort of squash top hat. Okay. And this is called Ohm's law. Voltage and current give a straight line graph through the origin. That means they're proportional. Things that are proportional have a nice simple formula that you can fit into like a whizzy triangle. And that would mean, anybody speak triangle? What's the formula for resistance? Well, here's the equation then. If I cover that up, what equation am I left with? And if you've not seen how these triangles work, to answer that question, you cover up the thing you're interested in, and it leaves you with voltage divided by current. If you've not done this in maths, it's really good, because equations can be written in three ways. Voltage is current times resistance, resistance is voltage over current, or current is voltage over resistance. Have you got to remember three equations? No. One triangle to rule them all. If you want to know the equation for resistance, because your physics teacher's asked 3 times and his arm's starting to hurt, then you cover up resistance. What you're left with, look, voltage divided by current. Let's try again. What's the formula for current? Voltage divided by resistance. What would be the formula for voltage? Current times resistance. If you've not seen triangles as a way of writing equations in physics, really useful. Instead of remembering three equations, you only have to remember one triangle. And the rule is you cover up the one you want. So if an exam question said to you work out the resistance, you would do voltage divided by current. Okay? And that's lovely. It's got Mr. Ohm's name in it at least twice. Would anyone like to comment on this piece of physics? I often call it this. Ohm's law. Have a look at the results you got last week. And Ohm's law. Does anyone have any comments to make? Ohm's law says voltage and current are directly proportional. If you draw a graph of them, you will get a perfect straight line. And also the light bulb one isn't a perfect straight line, is it? The reality is, this is reality, this is the actual experimental results. It's not just light bulb, there's a whole pack of other devices which you can connect up and you get completely not straight lines, okay? The problem with Ohm's law is it doesn't work. It works for some things, so it works, for example, resistors. Although, to be honest, if you get a car battery and connect your resistor to it and it explodes in a sheet of flame, as you take measurements as that's happening, will it be a straight line? Of course it won't. So it sort of works with resistors up to a point. It doesn't appear to work with light bulbs. And that's quite important because those light bulbs were just little swirly bits of metal. So it doesn't work with light bulbs, it doesn't actually work with anything made of metal. Now, how impressed are you with a law about electricity that doesn't work for metal things? That's not great, is it, really? Can you see this is very bad news indeed, and that's why I often put inverted commas around here. Yes, it's called Ohm's law, and the big tick we would put next to it is extremely useful because it's roughly right in many situations. The people who wired up this building will have used Ohm's law to work out what to use, and here we are, 100 years later or whatever, it's all working fine, okay? So it is a very useful, it's almost engineering really, it's a really useful rule for making things actually work, okay? So don't get me wrong, I'm not having a go at Ohm's law, but to say it's a piece of physics like the law of gravity or the law of motion, well look, it can't be. He's written all this lovely stuff, but this is only true, all this stuff is only true if you get a straight line graph. And you saw last week, many devices don't actually give a straight line. Okay? And Mr. Ohm had an answer for this. He said devices that don't obey Ohm's law, so your light bulb last week that gave a lovely curve, they have a name, these naughty things. They're called non-ohmic. What's the definition of a non-ohmic device, I hear you shout? The answer is things that don't obey Ohm's law. Can you see that's a bit... So there's things that obey Ohm's law, and the things that don't obey Ohm's law, well, they wouldn't do because they're non-ohmic devices. How do you know if something's a non-ohmic device? It doesn't obey Ohm's law. Can you see the whole thing is getting a little bit circular, isn't it? Yeah? I've invented a fantastic rule of physics, which is that things fall upwards. And you may say, hang on a minute, what about that object that just fell down? Oh yeah, but that's a kind of object that doesn't obey my law. This isn't good science, is it? This isn't really very good. As a piece of physics, as a fundamental law about the whole universe, Ohm's law really doesn't work very well. Okay? So you have to be careful with it. It is unusual for bits of physics in that it's strictly limited. It is strictly limited to ohmic devices. Only ohmic devices, only things which are ohmic, obey Ohm's law. Yeah? What things are ohmic? Well, resistors aren't bad. Resistors are mostly ohmic. Okay? Importantly, resistors in exam questions. If you're thinking, why is he teaching this utter rubbish? The answer is, the devices in exam questions are generally taken to be ohmic unless they tell you otherwise. So if you see an exam question with a resistor in it, then you can assume it's going to obey Ohm's law. Okay? Although you've seen with your practical work that pretty much most things don't. Anything with a decent amount of metal in it, as it heats up, it will change its resistance. Okay? Having said that, that's quite useful. As I say, in exams everything's ohmic, and also many things in the real world are fairly close to. Look at your light bulb one. How far away from a straight line is it? It's not a long way away. If you used Ohm's law to make predictions about your light bulb, you'd be wrong, but you wouldn't be wrong by much. And if you allow a bit of a margin for error, you could actually use Ohm's law to do some quite useful things. Okay? But anyway, that is Ohm's law. But you must be careful. It's not like gravity. It doesn't work for everything. It only works for things which are ohmic devices, which is a bit certain about it. Okay? Is everybody happy with that bit? Okay? Right, let's just do then Let's just do very quickly then a little bit more about resistors before I let you loose on some circuits. Okay. So 2 more things to write down. That's the good news. We just need to have a quick look at resistors. Okay. Resistors are generally assumed to be ohmic. Certainly in exam questions, resistors are ohmic devices. So you can assume that they obey the voltage, current and resistance triangle. Okay? If they give you a voltage and a current, you can work out the resistance using that triangle. If they give you a current and a resistance, you can work out the voltage using that triangle. Okay? If you try and use this with a real light bulb, or many other real electrical devices, it won't quite work. But as I say, resistors, particularly in exam questions, they have the advantage they obey this law. Okay? Which means they have to have a certain value. So you might, for example, get a 20 ohm resistor. I've got some here, I think. A little pot. Resistors can be made very small. If you open up your phone, take the circuit board out, the resistors in there are probably so small you'd need probably a microscope to see them. These are a little bit bigger, okay? But they're used to control electricity in all kinds of circuits, okay? Now, the interesting question is then, we know what voltage and current do in parallel, so to finish off our jigsaw, we just need to know what resistors do in series and parallel. And the good news is in series, it's very simple. Let's just draw one example, then you'll know it for the rest of your life. If you take 2 resistors, like that, then the total resistance of that would be 50. Resistance in series is very straightforward. You simply add them up. Okay? So if you're given resistors in series, all you have to do is to add up to get the total. This conglomeration here would behave as though it was a 50 ohm resistor. Okay? In parallel, things are much worse, unfortunately. The curious thing about putting resistors in parallel is you reduce the total. So let's take something like, let's have a 4 ohm resistor and a 6 ohm. Just draw these 2 examples and then you've got it forever. Those 2. Now the first thing to notice about that is it will have a total resistance less than 4. A good way, and this is good for checking your answers, when you put resistors in parallel, you always reduce the resistance. Okay? It's not a very good way of thinking about it, but you can imagine having a skinny little 1-track country road, and then you make it a bit wider into a 2-carriageway road, and then you make it into a dual carriageway, and then you make it into a motorway. You can see you're making it easier for the electricity to go through, whatever that means, which kind of explains why the resistance goes down. So the first thing to do if you've got this in the exam is to look at it and think, I know the answer is less than 4. By putting resistors in parallel, you reduce the total resistance. Okay? If you make a muck up on your calculator and get the answer 84, you know straight away it's wrong because the answer you get must be less than 4. Okay? Now there's an unpleasant formula for working this out, which is actually quite easy to use, but you've got to keep your wits about you, I think. The 2 resistors R1 and R2, let's just call them that for the moment. 2 resistors R1 and R2. How do you work out the total? Can you just add them up? The answer is no. You can add them up if they're in series, but in parallel you need to do something a bit more complicated. And the rule is, you times them, you add them, and then you divide those 2 numbers. The way I like to remember this rule is as the product divided by the sum. So if you get resistors in parallel, how do you work out the total? What's the product of the 2 numbers? What's the sum of the 2 numbers? And then you make a fraction out of that. If you think I might do that and I might get that upside down, it's easy to remember because P comes before S in the alphabet. It's product over sum, not sum over product, because P comes before S, isn't it? Yes, it does. Okay, so let's have a look then. What have we got to do? We've got to do 4 times 6 divided by 4 plus 6. Do you see? I multiply the 2 numbers, 4 times 6. I add the 2 numbers, 4 plus 6, and then I make a fraction out of the 2. 4 6 is 24, and 4 6 is 10. Everybody happy so far? And 24 over 10 is 2.4, don't forget the units. It's a resistance, so it will be in ohms as well. Okay? 2.4 ohms, is that less than 4? Yes, it is. Fantastic. Right, jot that one down so you've got an example of how to do it. Once you've done it a few thousand times, it's pretty obvious. But you can see the idea there, and top maths people next to you will be able to spot that you're always going to get a number less than the smaller of the 2. If you've got a number bigger than 4, if you've got 24, for example, you've obviously done it wrong because you've ended up with a number bigger than the smallest one. Okay. What would happen if they were both 4? We'll do that in the head. If they were both 4, 4 times 4 over 4 plus 4, what's that? 2. What if they were both 6? Be 3. What if they were both 10? 5. Anyone seen the pattern yet? What happens if the 2 resistors are the same? Half. Might want to pop that in your margin. If they're both the same, you don't bother with the formula, it's just half. 2 10 ohm resistors, total will be 5. Because 2 10 ohms side by side, the electricity's got a choice, is the equivalent of just having 5 ohms. If the 2 resistances are the same, you can do this by all means, but I can tell you for now, you're going to end up with an answer which is half the individual values. Okay, you might want to put that as a handy shortcut to put in the margin.